Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous videos, we saw that sample selection bias occurs when the observations in our dataset are not representative of the population we want to study. So what we learned was that OLS is not making a mistake. It's simply estimating the relationship using the observations it can use. So it's the data that's the problem, right? So the natural question becomes, can we somehow account for the fact that our sample isn't selected randomly? And the answer is yes. One of the most influential solutions in econometrics is the Heckman correction. Which was developed by James Heckman in 1979 and earned him the share of the Nobel Prize in Economics in 2000. And bringing back the familiar diagram, how do we apply this like Heckman correction in here? We had the population, and we had the selection process, and that gave us the observed sample. Until now, we've treated the selection process as something hidden. We knew it existed. We never tried to model it. We simply worked with whatever observations appeared in the dataset because that's the dataset that we were given. Now, Heckman's key insight was surprisingly simple in the sense that what it did is, let's not ignore the selection process. Instead of ignoring it, let's model it explicitly. Okay. Suppose that we go back to our usual model where we have wage as a function of education, but we only observe wages for people who are employed. So what determines whether someone is employed? Only those employed. And in terms of like what determines, it could be education, it could be experience, it could be age, health, market conditions, and so on. Okay. So employment clearly isn't random. It depends on this whole set of variables that are unobservable, okay, or other unobservable characteristics on top of the ones that we have listed here. And some of these characteristics, they also affect wage. And if only observed characteristic drove selection, we could control for them directly. So that wouldn't be really a problem. We've seen that with omitted variable bias. The way to solve it simply include these variables into the equation. Now, the difficulty lies with the unobserved ones, such as ability, okay, which drive both selection and the outcome. So before we can model wages, we first need to understand why some people have observed wages and others don't. So that is the first major conceptual shift that it's being introduced through the Heckman correction. We're no longer modeling just the outcome, we're modeling the process that determines whether the outcome is observed at all. Now, traditional regression takes the observed sample as given. Heckman's approach asks, how did we end up here in the first place? So it's asking two questions instead of one. We've got question one, who enters sample? And question 2. What determines the outcome? Traditional regressions, they will only answer the second question, and it takes the first question for granted. Heckman is going to try and answer both questions at the same times. Okay, so this two-question framing is the easiest way to think about the Heckman modeling without any equations. And if each of these questions was representative of an equation, then you'd have to solve them simultaneously, meaning solving a system of equations. And the Heckman model basically is doing that through these two questions. So question 1, the outcome equation, and question 2, the entire structure. The selection equation, we model the probability that an observation enters the sample at all. Okay, so probability an observation enters the model at all. And the second, the outcome equation. So let me just add, so this would have been the selection equation, and this is the outcome equation through the question. The second one is going to estimate the relationship of interest, but taking the selection process into account. The two equations are estimated together because the same unobservable factors drive both of them. Okay, so together as both affected by same unobservables. If we understand how observations were selected into the sample, we can estimate how the observed sample differs from the full population. Once we account for that difference, we can correct the bias in the regression. So the correction doesn't create new data, okay? It uses information about the selection process to adjust for the observations that we don't see. Imagine you're trying to estimate the average height of adults, but you're only allowed to measure people who can't fit through a certain doorway that is only 1.8 meters tall, okay? So you've got this doorway, this is only 1.8 meters tall, and you've got people basically going through it, and you want to measure the height. So it's very clear here that many taller people will be excluded because they won't be able to go through that door, okay? Now, if someone tells you exactly how that door works, that it's the threshold 1.8 meters and so on, you know the precise height of that threshold. So now the door hasn't disappeared, it's still in there, but now we understand the rule with which you go through that door, which means that you can begin to also adjust your conclusions based on that. So you know in this case that you are systematically missing the tallest people, and you can correct for that. And that's essentially what the Heckman's method is doing. It uses knowledge of the selection rule to correct for the systematic gaps in the data. And to those of you who the follow-up question is, well, why is OLS not enough? Well, keep in mind, OLS assumes that the observations it receives are representative of the population. So OLS is not an AI process, and the softwares that run the OLS, this mathematical process, are not AI either. So when the sample selection is present, that assumption has already been violated before the regression even begins. So rather than ignoring the selection process, Heckman's method incorporates it directly into the estimation. The one sentence key takeaway out of this video should be that the Heckman correction addresses sample selection bias by explicitly modeling the selection process, using that information to adjust for the systematic differences between the observed samples and the full population. And now that you've seen the intuition, if the sample was selected according to a systematic process, we know that we shouldn't ignore it and we should model it. And in the next video, we'll introduce the key ingredients that makes this correction possible, which is the inverse Mills ratio, and why adding it to the regression removes the selection bias. So stay tuned and I'll see you in the next video.